take some more achievement related to the control with short time and take a longer time for fusion. We can try to keep the good for detach with the V-sharp and reduce the temperature very high with the high technique like this. Okay, again, thank you very much about your very presentation. Okay. The next one, I'd like to invite Dr. Vũ Thanh Mai from Vietnam University of Science. With the name of presentation is study on the impact of NDFB 7.1 nuclear library uncertainty on the CMAT fuel ADS calculation results using Monte Carlo methods. Please, Thanh Mai, now you begin. Okay. No one hear you because then.
Okay, so good morning, everyone. So it's my pleasure today to present our research data on a study of impact of NDFB 7.1 nuclear library uncertainty on the field ADS calculation results using Monte Carlo method. So this is a part of the research we done for the ADS design project, today talk, I would like to talk first, I would like to introduce about our motivations of our research. And after that is the brief introduction about the ADS system and the summit field, and also the ADS core configuration also will be described. In here, we also give some information and also the calculation condition, the simulations we have done. After that, we would like to discuss about the sensitivity and uncertainty of summit field ADS. And finally, some conclusions. First, I would like to start from the motivation of our research. So as you here may all well aware of the benefit of nuclear power in secure the power supply for the economic growth, because the nuclear power is clean energies and reliable power option. So like nowadays, a lot of country utilizing the nuclear power. However, nuclear power still remains some issue, such as the nature resource limitation. By this, I mean the uranium natural resource, because we cannot use uranium forever. So I think it's necessary to find alternative fuel to replace the thorium, extend the nuclear power utilizations in the futures. And the next one is the cost of the power production. I think we always look for a cheap power option, and especially it's very important for the country like our country, the developing country. So power option which is reliable, sustainable, and cheap is very important. And the third issue we think is the spent fuel management, and with the very high decay heat and also the high level of radiotoxicity, so spent fuel from nuclear power plant is really hard to treat, and is considered as the drawback of nuclear power when some country consider it. So in our research, we're also looking for solutions for this issue. And the last but not least is the safety, especially the safety of the operations. So in our ADS design, we are considering to put thorium fuels and reprocess fuel from the spent fuel of the light water reactor into the ADS system. So by using thorium fuel, so we can think like we can replace the uranium fuel, not using uranium fuel anymore in our reactors. thorium fuel actually is not a fissile material. It's the fertile material. So in order to put it into a reactor, so in this ADS, it's very special. We can use a neutron from the ADS to convert thorium into uranium-233, so that we can use thorium to generate the power from the fission reactions. And thorium fuel have a higher burn-up capability, so we can burn it in deeper level. So it helps to reduce the cost of the power productions. And also thorium fuel, because of this decay chain, so it have low transuranic element generations. So it helps to reduce the TIU, the transuranic elements. And besides thorium fuel, we also put the reprocessed fuel into the ADS in order to transmute it into the low level of radiotoxicities, and also shorter half-life isotopes. So in here, TIUs including neptunium, plutonium, americium, and curium was recovered from water reactors and put into the ADS to transmute. So in order to design a reactor, especially Monte Carlo simulations. However, the simulation result reliability is dependent on the nuclear data. So we think it's necessary to check for the reliabilities of the nuclear data. So in this today talk, I would like to give the information about our study on the uncertainty qualifications. And in here we use two kind of Monte Carlo method code. One is the MCMP6 Whisper, and another one is the Scale 6 code. So in this figure, I would like to give the schematic view of the ADS system. The ADS system is included three main components. The first one is the subcritical core. This is the subcritical core, and inside it, it have a spallation neutron target. So we use accelerator to accelerate the proton into very high energies, and we bombard the very high energy proton into the spallation target in order to produce the spallation neutron. This spallation neutron help to maintain the chain reactions in this subcritical core. So the scope of our study is just within this subcritical core. So in my previous research in my doctoral thesis in Osaka University, I used thorium field and TIU, which is the reprocessed fuel from like water reactor, to put it into this subcritical core. However, at that time we use a thorium oxide fuel and TIU oxide fuel, but we do not put it into the same assembly. We put it separately into a seed and blanket ADS, which means in this seed TIU used to initiate the fission reactions, and this blanket fuel we use it as a breeder in order to maintain the subcritical level of the ADS. However, we found that this oxide fuel, especially the reprocessed fuel, this will give the very different power distribution between. This is a fertile fuel, right? So at the beginning of the this fertile fuel produce very little power, so it gives a very high power peaking factor. So in this study, we consider to put in a diluent fuel like a CERMET fuel in order to reduce the power peaking factor. So what is CERMET fuel? So by these schematic representations, I would like to give some idea about the CERMET fuel. So in here, there's fuel canals. We use TIUs, which is plutonium and minor actinide oxide. And for the CERMET fuel, so in here as the metric of the field. So with this field design, we can reduce material density in the fields and reduce the power peaking factor. So the summit field is help to stabilizing the field at the very high temperatures, and also it help to improving the thermal conductivity, and also it's provide more space, which is the metric, in order to accommodate the fissile products. And very important, which is I mentioned in the previous slide, is reducing the power peaking factor inside the ADS. So by using summit field, we can burn it into higher discharge burn-up, and we can utilize the field longer and can produce more energy using this kind of field. And this is the compositions of the summit field. So this one is the this is the TIU. It's called, recovered from light water reactors, and this one we use it from 45 gigawatt burn up per ton from the light water reactors. We put it after 10-year cooling inside reactor, and now we recovered these TIUs and then put it as the fuel of the ADS. And here is the vertical and horizontal cross-section view of the ADS we use. And in here you simply can see the thorium fuel is the green one, serve as the blanket, and the seed is the ripple set fuel assembly, which is the purple one. And the light purple here and here is the lead bismuth eutectic. This used as the spallation targets and also a reflector of the core. And in here we use sodium to serve as the coolant. In this table, I show some main design characteristic of the summit. So the power of the ADS was set into 500 megawatt thermal, and we use of 144 thorium oxide assembly, and then we use 102 TIUs, which is a summit fuel assembly, to put it into the reactor. And here is the neutron spectrum we obtained for the summit field using MCP6, and we can see this one. This is the fast spectrum reactor, because we found that the fast spectrum is have very benefit for transfer the TIUs elements. And in this presentation today I only talk about the uncertainty quantification for the ADS system, and in here the uncertainty for the system was calculated as mentioned in yesterday talk of Mr. Nam. So we simply use the same as follow, and each element in here, the sandwich rule, we use the sensitivity and conversion metric. So each element of the sensitivity metric, we use these equations, and this can obtain by Monte Carlo method code, for example, like MCNP, serpent, or scale. And in here, the conversion metric is the group structures. And then we can also obtain it from the nuclear data library. We can download it from the nuclear data library webpage, and then we use the neutron data processing code like NGàY, and then we put it into group structures. So as mentioned in this research, I use two kinds of code in order to generate and estimate the uncertainty. First one is the scale. So in scale, we use a Kino module in order to give the K effective value, and then the SAM to produce the sensitivity. So we have the sensitivity metric, and the conversion metric in scale, it has the ENDF B7.1 56 group, which is included in the code, and then we can use it in this conversion metric, and then put it as the input into the tsunami model to estimate the uncertainty of the system. In the MCNP, actually we use MCNP6 in order to generate the K-effective and sensitivity. But in Whisper, it have 44 group building for ENDFB 7.1. The group structure is quite different compared to the previous, the scale one. And then this one is put it into the Whisper. Whisper is the module which is distributed along with the MCNP in order to estimate the uncertainty. However, as we can note it here, 44 group structures and 56 group structure is more favored to use in the thermal spectra. So in here we have the fast spectrum system. So we use it as the primary research, and then actually we would like to generate by ourselves the fast group structures in order to obtain the more reliable data for the ADS research. However, in this study, I'll present the data using this 44 and 56 group. And here's the result of the uncertainty for SURMET ADS obtained by Whisper and Scale. And here's the reactivities. And this one is uncertainty. And we look at here, the uncertainty K-effective is like 1,300 PCM. And this one for Scale, we obtain is almost about 900 PCM. So we think this one is significant. And by compared it with the target accuracy, this one is published by NEA, and it said for the target accuracy of K-effective is only about 300 PCM. So this uncertainty gives like more than 4 times compared to the target accuracy. So we think like we cannot remain the K-effective results from the simulations like this. It's too big. So we should find a way to adjust the nucleic data and reduce this uncertainty. And in order to doing so, we'll do the breakdown research in each isotope. This is the uncertainty of the isotope wise in this table. So you can see that the largest contribution to the uncertainty of the ADS is from Neptunium-237. The next one is Plutonium-239, Americium-231, and so others. In here, we also notice that Molybdenum-95 also gives a big contribution to the uncertainty. So in order to understand where is the uncertainties come from and from which energy region, so I brought here the sensitivity profile for the some reactions belong to those above mentioned isotopes. So this is total nu for Plutonium-239, and this one is fission of Plutonium-239. This one is the total nu of Neptunium-237, Americium-241, Plutonium-241, and Plutonium-241 fission. And in this is the largest sensitivity area. We can see it's located in this pink area I plotted here. This pink area, which actually means the neutron spectrum of the system. You see this sensitivity profile is reflect the neutron spectrum of the system, and it's located into at the resonance and the fast energy range. This is the contribution of the positive sensitivity. However, in order to get the uncertainty, actually it's also related to the cohesion metric. So in here I plotted them. In here is 6 reactions. This one is the accordingly 6 reactions, the cohesion metric, and the uncertainty is multiplications of sensitivity and cohesion metric. So in here we take attention on the area which have high, which have large conversion metric. In here we see in this color, I don't know whether it may hard to recognize, but in here is in the first region we see the lighter blue color here, which is the larger conversion metric values, and in this area we see very small here, but in the very fast energy range. And in this also, this is almost for this plutonium 241 is almost in the every is from the thermal to fast energy range. However, in the fast energy range, it have larger conversion metric, and in this one also. So for those reaction, it's recommended to give more attention and also do the adjustment for the nuclear reactions of those reactions at the large and at the fast energy range. And this is the negative contribution. Actually, it's converse, but we can see it's also reflect the neutron spectrum of this spectrum of the system. And similarly, I plotted the conversion metric here. So in the fast energy range of those isotopes, we should pay more attention for those isotopes in order to achieve more reliable simulation results. And here is the comparison of the sensitivity we obtain by MCNP and scale. So this is the equal lines, which is the value equal to 1, and we see that the sensitivity we obtain by MCNP and scale is very consistent. So the uncertainty, the difference in uncertainty, we think that is come from the difference in the energy structure, which is the 56 and 44 group structures we're using in MCNP and scale. So I'll come to very brief conclusion for my presentation today. So the impact of ENGF B7.1 nuclear library uncertainty on the Surmet field ADS core reactivity calculation was investigated using 2 core systems, and the uncertainty was found to be significant. It's about 1000 PCM for the Surmet field, and from the sensitivity, we found that the uncertainties mostly come from the total new and fission reactions of the plutonium-239 to the new and reactions of plutonium-241 to the new of
this is the reactor, and they are in the nuclear in the control system include 3 UNO. This on the right hand, you can see this detail of the UNO is called ASUS14. They are the in the reactor including fission chamber and the ionization chamber, and this using the amplifier and the frequency up out of the reamplifier. You come to the UNO, and this calculates the reactor power and reactor periods, and also the reactivity, and this generate the alarm signal to shut down reactor by this cut off electricity of the servo motor. In the nuclear research, the equation the reactor power is a KSR coefficient, and this frequency FSR frequency output from the reamplifier. This the reactivity is very important. So you can see this reactor is critical state or operator as the state power when the K efficient about 1. But if the coefficient is smaller than K1 is subcritical or operation as the power level is falling. And if the coefficient is more than 1, is supercritical, or we change reactor power level. This is the equation about the reactivity with Kf effective. The time behavior of the reactor power level in the nuclear reactor changed by the K effective can be expressed by the point kinetics equation. So in equation 3 and 4, this PT is reactor power as the time t, and this PT is mean the reactor reactivity as the time t. And this concentration of the group, 6 group of delay neutron. And so you can solution of the equation 3 and 4. So you can have the equation 5 is used for develop to calculation the reactivity, and is used for calculate the reactivity for the nuclear research reactor. So we use this PM and PM -1 is mean the history power. So you can see table 1. Is the table 1 is the kinetics parameter of the nuclear research reactor. So we use all of information about the parameter for the equation in the equation 5 to calculate the reactivity. This is the way we use FPGA TIS7 to calculate the reactivity. And you can see this Fs is the frequency output from the reamplifier. So it's sampled by FPGA. So the frequency is very flux. So you can calculate this mean the mean of the frequency. So we need the filter, and the S1 to S6 is mean the you can see this in the equation 5. So you can see this is of a 6 group neutron. So you can so you can calculate the six up equation. So usually in the FPGA we use micro-base 32 bits to calculate the reactivity. After that is send the data to the PC. This is a flowchart of the reactivity calculation in FPGA at TIS7 in which embeds with micro-base. This we enter the parameter of the SIG1 to S number 6, and recently the PM is mean the reactor power and the after filter, and we calculate the reactivity and send reactivity to the PC. In experiment we use PGT7R is used in the dialog reactor for testing with and compare with the comparison with the input PNO 1 to 121 as 5 module using dialog control system. This is schematic overview. This generator, this the frequency. After that, the frequency sent to the PNO is used in the control system and the FPGA pay. So after that, we calculate the reactivity and send this the values to the computer to data login. And these are the, you can see this is a rest and is a rest is color is used for the import module, and the black color is using FPGA. So we can pair this the import module and the design modules agreement with together. We testing us the we generate vector periods with the 80 second and 120 second. So this aiming this reactivity we test with reactivity is positive. And we also test with the reactivity with minus periods. And also we this in the table 2 this compare with the FPGA and the import module, and we also testing by the inverse how equation for with the double periods. So you can see this is agreement. And in school conclusion, the digital reactivity meter module was designed and construct the output for the outputs from the amplifier with proportional with the reactor power and the sample and filter in the FPGA using FPGA. The task solution points reactor kinetics equation to calculate the reactivity and perform with the parallel on the FPGA hardware and the embed in the microcontroller. Experiment results of the measure reactivity by FPGA module does compare with the import module using in the nuclear research reactor. And they are the first step for the in the next year we will test some experiment with the ROP and we compare the module was designed and construct when in the on the reactor. Thank you very much.
Okay, thank you very much for your very nice presentation. And now the time for question and recommendation or comment. Anyone have the question?
Dạ vâng ạ. Chắc em cũng hỏi bằng tiếng Việt. Dạ em cảm ơn, thấy bài rất là thú vị, và có đặc biệt là em muốn thắc mắc là cái bộ lọc của anh là anh xài trung bình để lọc đúng không ạ? Thì em đang thắc mắc là anh đã có thử các bộ lọc khác không, và kết quả nó ra như thế nào, hay là anh chỉ có làm một cái đó thôi ạ? Em xin hết.
tiếng Việt luôn ha. Vậy là hiện nay thì trên để mà đưa cái tín hiệu, khi mà mình lọc các tín hiệu vào thì có sẽ rất là nhiều bộ lọc, từ command, bộ lọc moving average rồi các thứ. Nhưng mà hiện nay để mà càng đơn giản, cái bộ lọc mà càng đơn giản mà để cho cái việc xử lý đáp ứng nhanh á, thì người ta sử dụng moving average là đa số, tại vì nó vừa đơn giản mà vừa dễ thực hiện nữa. Còn nếu mà sử dụng các cái bộ lọc ví dụ như command hoặc những cái bộ lọc butterfly á, thì nó tính toán các hệ số nó cực kỳ phức tạp và nó rất mất là nhiều thời gian, cho nên là đa phần người ta sẽ sử dụng cái moving average là tính toán. Sample rate mình có thay đổi được. Tại vì cái sample rate này nó quan trọng là khi mà tần số lối vào mà nó ít á, thì mình phải tăng cái sample rate lên. Còn khi mà số đếm nó đủ lớn rồi thì mình giảm cái thời gian nó lại, và nó sẽ tự động.
Any question? So again, thank you very much. And the last one is this morning, Mr. Trương Hoàng Tuấn, with the name of presentation of maximum cladding temperature, evaluation of various thermohydraulic models for the nuclear research reactor VVRSM Tascam using best estimate code relap 5 mode 3.3. Okay, please.
Good morning to the audiences at the premises and also the participants on the Zoom online. My name is Trương Hoàng Tuấn, as you can see on the screen, and I'm from the Center for Nuclear Technologies. Today, I'm honored to present to the evaluation of the various thermohydraulics models for the nuclear research reactor VVRSM Tascam using best estimate code RELAP 5 mode 3.3. So here's for the today talk. Firstly, I'm talking a little bit about introduction, actually about myself, and the purpose, the motivation of this presentation, and a little bit about the VVRSM and the fuel that it used, the IRT4M and the RELAP 5 model that we have built and simulated, and also the field results. So here, I repeat myself, that's my name, you can see on the screen, and I'm from Ho Chi Minh City, Vietnam. So first and foremost, I would like to mention my background education, because I'm not really from, like, I didn't have a nuclear engineering background, and I graduated as the aerospace engineering, and also another degree in commerce. So your comments are very welcome, because my understanding on the problem on everything might be partial or incorrect. So I need to fix that ASAP. So the purpose, firstly and foremost, we are going to have the RCNS project soon. So it's a collaboration between Russia and Vietnam, and in there, there's a proposal research reactor, roughly around 10 megawatt. And that new research is based on the Russian technology. So if you look in the world right now, we can see that the VVRSM is the one that's quite similar to what we might be looking at. So by learning those, like from the reactor that have long history of running and operating, we could understand more about the thermohydraulics. And as well as, like, we would like to develop a group at the Center Tech, that's where I'm from, with modeling and simulation capabilities to support the RCNS projects in the future. So here, a little bit about the reactor that we are looking at. So you see, actually at the Institute of Nuclear Physics in the Republic of Uzbekistan, and it's in the city Tashkent. It has been operating like since 1979, so it has really, really long history and experience. And as I said earlier, the nominal power is like 10 megawatt, and previously it started as the high enriched uranium fuel, but soon later it's convert into the low enriched uranium, which is the IRT4M. So in here on the right, you guys can actually see the elevation view of the research reactor. It's only actually the tank. And so how can I put this way? It's really hard for the online viewers, but I will try to give some cues to follow. So if we look at the diagram, we can see that we have the central tank that's situated inside a tank with the diameter of like 2.3 meters. Yeah, I really can't say anything there. And in the central tank, we have the reactor core with the diameter around like 682 millimeters. That's situated like offside to the left, like on the screen. And we can actually, the coolant type is the water that is going into the inlet, goes up and turn around, and it goes through the reactor core. And in here, interesting design of the reactor is that the central tank and the coolant in the central tank and the coolant in the housing tank, they are separated and not mixing at all. And the water that going into the central tank around like 45 degrees Celsius. And in here, I didn't mention it, but I think the flow rate through it, the whole system, like the central tank, is around like 1,300 something meters cube per second or something. Yeah. So continue. Here is actually, you guys can see the reactor core that's situated offside. And this is a 20 fuel assemblies of the IRT4M. And actually, you can see the brown things here is actually fuel assemblies. On the rim, it is actually, I don't know what they are, but they might be a holding experiment or something like that. I couldn't find any information on those, so it would be helpful if someone know and tell me what they are. In those, in the fuel assemblies, I still have no idea where the controllers are either. Like, no paper mentioned on that. So I really need someone to fix that as well. In here, I will talk a bit about the ITR4M. So IRT4Ms, they have two designs, like the 6 tubes or the 4 tubes, the 8 tubes. But in here, for the Tuscan, they only use the 6 tube. And the structure inside, they are actually supporting structure for the control rod or for the experiment holder, something like that. And I have done some modeling effort on this RTM and noticed that, like, without this structure or with it, it doesn't affect much on the solution of your calculation at all, because these, they in the steady state simulation, they balance, like the temperature, we reach equilibrium, and it's not a sink or the source, the heat sink or heat source, so it doesn't affect much. So we can safely ignore these in the simulation. And here for the relap model, I actually model just the center tank, because the design doesn't mix the water from the housing tank with the center tank. So the center tank, we can actually see they are from component 0.001, 02, the core, and the 3. For the vessel core, we split up into number 4 and 5. Oh, this design is really interesting, because initially I split it up into a 2 water column, and they have the cross flow like from number 5 to number 4. Then later on, I read some Chinese paper that they have done not exactly on this reactor, but on different experiment, and they have this kind of modeling effort. So I tried it, and I found that the results are quite similar, but these looking easier to input in the relapse. So I chose these instead. The heat exchanger, like I do have information on it, but I don't know how to properly like model it. So it's still a work in progress. So for right now, for the heat exchanger, I just simplify it as the inlet and outlet. So it doesn't like for the steady state calculation, it might be good enough, but for the transient or any accidents modeling effort, it might be not accurate enough, or it might be wrong. So in here, what I did is the sensitive analysis on the meshing of the component core here. So I did 3 different modeling on this. So the first thing I did is like 7 error channels represent in here represent 7 fluid flow between 6 tubes. Or I can split into, like the second model, I split into 7 average channels and 7 hot channels. And the last one, I did the whole simulation of the whole core using REACTOR 5. So in here, another problem here is that the fuel we have is actually the square that they share the same concentric they are concentric square tubes. So for relapse, we can't do that. We have to convert into the circular one. So in here, I try to preserve the perimeter of the square to with the circular perimeter, so they are actually equals. And since the different parameters here, they would actually change the volume of the water flow. So however, in the modeling effort, I try to preserve like when I input the volume, like the area of the fluid flow, I try to match with the square tubes instead of circular tubes. So by doing so, we can keep up with all the other fluid parameters, such as like the hydraulic diameter and stuff. So we don't have to convert it into some different quantity using the equations. We have to come up somehow. And here the thermal power in percentage of the whole reactor core. So because we only have 20 fuel assemblies, so in the 4 corner here, we don't have, so they actually zeros. And by the design, like actually I got this number from a paper in 2020 from a group, and they did a calculation and they got this number, and I just took them out. So I don't really know how they calculate it. Like they didn't say anything much. And here again, like they also did a really well on the calculation, like the power density on one fuel rod, like on the, so I took that as well, and I normalize it and input into REACTOR 5, so we can actually have a really nice curve along the axis of the fuel assembly. And in here, we can actually see that due to the control rod position, we can actually see that the picking power is actually pushed down toward the bottom of the fuel assembly. So it's my reasonable to see this might be correct graph. Next. So in here is because I said that I calculate the steady state, but to be sure, I also did the transient on the model to determine that if my model is good enough, if the model could reach the thermal steady state. So in here, I initially start with 45, like the whole system. They start on the pumping and stuff, and the temperature of the outlet is actually at 45, which is reasonable because the core is not running. and instantly I raise the power to maximum power, like 10 megawatt. And after 6 seconds, we can see that the outlet temperature reached around 52 degrees. So since I don't have the power curve of the startup, so I just try to. That's why I changed it. That's why I chose to use that kind of changes. If I actually have the power curve of the startup of the power reactor I think we could have a proper nice curve to present actually how the system start up. So in here I got the numbers like 52, which is like 1 degree hotter than the experiment that they have done. And also another thing is I also did the calculation of maximum clouding temperature as well. And this is actually is not an experiment value, but it's actually someone else did the calculation using bullet temp, and but bullet temp was only calculate the reactor core, but with the relap we can actually calculate more than just the reactor core, the whole system. And when I compare to it, and we can actually see that the average channels could not predict the maximum clouding temperature correctly. But however, if the meshing is more fine, we can get the better result. However, for the 140 channels model is actually really costly. As you can see here, like the result is not much different, like slightly different, like 0.1 to 3, might be due to error and stuff. But however, we can see that the cost, like in terms of calculation cost, like how much how long does it take to do the calculation, and you can see that it's jump up like around 50 times more. And here is lastly the plot of the whole reactor core, like the fluid, the thermohydraulic of the reactor core, so using Excel. Represents here. It's not to scale because you guys can actually see that in the middle here is not big enough to present the correct size of the fuel. Next, actually I missed the conclusion. The conclusion here is actually, if we look at here, it might be good enough to use the average 7 average channels and 7 hot channels to simulate further to determine the maximum clouding temperature. And also there's because I couldn't because to achieve more accurate, I need to find somehow to model the heat exchangers and include in the model so we can evaluate on the different chances on the different accidents with more confident results. So these are my reference, and thank you for listening.
Okay, thank you very much. It's very good. When I application of relapse fight to the touch scan reactor, even presenter they don't have so full information. So okay, it's the first step, and so please ask question and any comment.
Well, maybe I have some comment or suggestion. Let's go back to the slide that you have the curve of the increasing of temperatures right here. Yeah. Yes, it's for calculation. You can use that, but in the reality, I think because we don't in the experiment, we don't increase the power like this step by step, right? And to do so, in the calculation, I think you use like inlet or outlet. You use time dependent volume, right?
Not really. I think okay, it's interesting because the way that I do this is like, I don't know why, but it's really weird. But the inlets, they actually the time dependent, but the outlet is not. So it's actually free. because I don't really have, like, we do have the whole system that running as a 1.35 bar. It's like 135,000 Pascal, the whole system. So if we let the inlet pressure like that, and we just let relapse freely calculate the outlet pressure and temperature, is more better that way, I think. Because if we can strictly, if we use the time dependent volume here, then the solution actually, like when relapse does the calculation, the value in the inlet will propagate down here, like on the way here. And also, if we have the time dependent volume here, then the value here will propagate up. So we have that kind of calculations. But however, when I try, but without using the time dependent volume in the outlet, we can have like nice solution preparation from the inlet on the way to the outlet. So that's slightly different. Yeah. So because we don't have the pressure rock in the reactor core, so we might don't have the correct pressure at the outlet at all. So that's the thing that we need to fix, like on the geometry set and stuff like that. So yes.
So I think it's good, you know, because now we don't have. I mean, Tuan doesn't have much information about the system.
I agree.
But
I absolutely agree.
you know, he's trying to
I
do
think
some
the first step to make an exercise
is quite good.
Very important.
I think so.
And you know that if we have the full scale, full information, full data, and so it's very easy to make a model in relapse. We don't know and we don't have, and so that's I think that's enough. I believe that.
Nó tính cho
Anyone?
Tôi xin có một cái comment này cho Tuấn rồi. Trong cái bài tính toán này của Tuấn thì cái mô hình này nó tương đối đơn giản. Nếu mà làm relapse thì đúng là không phải chỉ relapse mà các cái code khác tính cho cái trường hợp steady state như này thì rất là dễ. Tuy nhiên thì Tuấn trong cái bài trình bày thì Tuấn nên phải chỉ rõ ra các cái correlation cho tính toán truyền nhiệt đấy. Là phải xem thực tế là relapse nó dùng cái correlation nào. Và như kinh nghiệm ở Đà Lạt ấy, thì thường là chúng tôi phải sửa các cái correlation đó, bởi vì các cái correlation đó nó phát triển cho các cái dòng nhiên liệu như MTA, rồi những cái nhiên liệu của châu Âu cơ. Nhưng mà sang đến cái nhiên liệu của Nga ấy, cái hình học của nó sẽ khá là phức tạp, rồi mình lại phải chuyển nó sang thành hình trụ hóa, là một loạt các cái như là đường kính thủy nhiệt, rồi thể tích, cái diện tích dòng chảy ấy là mình đều phải mô hình hóa lại, và nó sẽ có những cái thay đổi. Nếu mà áp dụng các cái mô hình mà của các cái loại nhiên liệu MTA các thứ mà dùng ở trong relapse thì có thể có những cái nó sẽ sai đi rất là nhiều đấy. Và ví dụ như ở Đà Lạt thì các anh ví dụ sử dụng cái cool load là các anh phải sửa đi các cái correlation đấy. Và cái này là một cái mà trong tương lai ấy, khi mà mình xây cái lò mới ấy, thì mình chắc chắn là mình phải xem xét lại các cái correlation mà liên quan đến truyền nhiệt cũng như là tính friction ở cái loại nhiên liệu mà của Nga ấy. Thì đấy là một cái khuyến cáo thôi, nhưng mà nhìn cái kết quả tính cho cái steady state như mà dùng relapse file như vậy thì thấy là ok đấy Tuấn ạ.
Cái này phốc rồi anh Tuấn nên không sao. Cái này nó xin lỗi tiếp lời anh Tuấn, thế này có tiếng Việt thì có người Nga. Tất cả correlation tem bọn mình cũng có đã tính thử cho loại VVRKN và lẫn cả IRT này nữa thì nó đều là ok cả. Nên nếu tham khảo cái cách tính một loạt các correlation mà nằm trong VOTem, trong version cỡ 4.2 trở lên họ đã có ghi ra tất cả các công thức rồi. Mà bây giờ mình có source code của relapse rồi thì chuyện đấy mình có thể modify rất là dễ dàng. Đấy không có gì là khó khăn cả. Tuy nhiên là cái này thì nó như là bài thực tập thôi, nói thẳng thế, chứ còn những cái bước tiếp theo sau thì nó còn phức tạp lắm, còn nhiều khê lắm. Còn tính như thế này thì không thể nói đùa, chứ không thể chơi mỗi cái công thức mà gọi là phân bố công suất thế là ok đâu, không phải đâu. Nó phức tạp rất nhiều, nó cầu kỳ hơn rất nhiều thứ trong đấy. Tuy nhiên là cái mô tả của Tuấn ở đây vẫn là cái kiểu hình trụ đấy chỉ trong PLTM được, nhưng mà trong lúc này phải chuyển thành dạng tấm hết. Lúc đó phải cắt ra thành dạng tấm hết thì nó mới đúng trong cái lab mô hình đó còn tốt hơn nhiều. Cái đó chắc mình sẽ bàn sau, không chi tiết ở đây được. Ok.
Cường ơi, cho em xin ý kiến được không ạ?
Được, Trâm à, mời.
Vâng. Tuấn ơi, mình nghĩ là với kinh nghiệm của mình làm Relab ấy, bạn cũng mới làm mô hình một cái này thì thực ra bạn cứ tập trung vào cái bài toán này và bạn cố gắng để cho nó có kết quả cũng như là thông tin tốt nhất ở chỉ ở trong cái vùng hoạt trước đã. Sau đó bạn coupling, tức là bạn có thể phát triển thêm cái phần steam generator ấy, phần đấy làm cái phần tiếp theo nhưng mà nó không quá quan trọng. Nếu như bạn đã có được một cái quan trọng rồi thì bạn có thể phát triển những cái hệ thống khác nữa, chứ bây giờ kết quả của bạn bây giờ cũng chưa có thể chuẩn lắm, thì bạn chỉ tập trung vào cái này cái đã. Thì đấy là cái cách học tốt nhất của bạn, chứ bây giờ mà bạn phát triển cái hệ thống nó rất là loạn trong đấy thì gần như là nó rất khó để control cái kết quả ban đầu của bạn. Thì đấy là ý kiến của mình qua kinh nghiệm mà mình xây dựng cái code ấy. Vâng, xin cảm ơn.
Cảm ơn.
Dạ vâng ạ, em xin cảm ơn ạ. Dạ.
Xin hỏi một chút được không ạ?
Xin hỏi. Dạ, xin mời anh nào hỏi.
Vâng ạ. Xin chào bạn Tuấn ạ. Dân ở bên Bộ Khoa học Công nghệ thì mình chỉ có một comment rất là nhỏ thôi. Thế là mình xem cái bài trình bày của bạn ấy thì rất là hay. Cái phần bạn chuyển từ cái dạng hình vuông sang hình trụ ấy để bạn tính ấy, thì mình thấy bạn có nêu là ở đây bạn cho hai cái perimeter đấy là nó bằng nhau, đúng không? Thì nhưng mà theo như mình hiểu thì đáng lẽ là phải cho hai cái đường kính thủy lực nó bằng nhau chứ nhỉ?
Vâng ạ, thì cái
đấy mình phải đảm bảo cái đường kính thủy lực trước, chứ còn cái perimeter thì mình phải điều chỉnh như thế nào để cái đường kính thủy lực nó đảm bảo nó bằng nhau, thì lúc đấy thì nó mới đảm bảo được các cái tính chất về mặt thủy nhiệt đấy. Đấy thì mình chỉ có comment đến thế thôi, còn mình cũng cảm ơn.
Lời luôn cái câu là tại sao lúc đầu là mình phải giữ vững cái perimeters, tại vì nếu mà mình nhìn cái phương trình truyền nhiệt của chất rắn sang chất lỏng á thì mình sẽ tính toán cái heat flux. Và cái heat flux đó là nếu mà heat flux thì theo cái đơn vị của mà Relab sử dụng á thì nó sẽ nhân với cái chu vi và nhân với cái chiều dài. Nếu mà mình không giữ cái chu vi chính xác á thì mình có thể là cái truyền nhiệt ở trên cái bề mặt đó của mình sẽ lớn hơn hoặc nhỏ hơn, nó có sai số. Còn đối với cái việc mà tại sao mà mình có nói luôn là tại sao mình cố gắng giữ mấy cái khi mà đổi sang từ hình vuông sang hình tròn á thì dẫn tới là mình giữ cái chu vi lại, nhưng mà cái diện tích mà đường nước á thì mình phải giữ lại cái giá trị cũ. Tại vì đối với thủy nhiệt á, khi mà nhiệt nó truyền qua cái phần thủy á thì lúc chất lưu, vâng, dạ, khi mà nhiệt nó truyền qua chất lưu á thì nếu mình giữ cái diện tích đó mình sẽ giữ được cái volume, cái thể tích mà vật chất, cái chất lưu nó di chuyển, thì lúc đó thì mình có thể không cần phải tùy chỉnh lại mấy cái đường kính thủy nhiệt cho nhiều lắm. Đó là một cách nó nguyên lý căn bản thôi, không có gì hết rồi. Xin hết rồi.
Again, thank you very much. And so we finished this section A in this morning. Chắc tiếp theo là có cái chương trình là mình sẽ đi chấm mấy cái poster. Chắc mời các anh tham gia trong ban mà được phân công nó chấm poster rồi xong ta quay lại đây, vì nó có thế này. Báo cáo các anh luôn là ta có phải một bài xuất sắc trong 12 bài. Poster mình sẽ chọn một bài. Dạ. Bên này thì 2 bài, một bài trẻ nữa. Một bài xuất sắc chung và một bài trẻ nữa. Ta có 2 bài, tức là 12 bài oral và 3 bài poster, thì 3 bài poster lấy một bài poster xuất sắc rồi. Như vậy ta sẽ có mỗi section sẽ có 3 bài. Cái này thì chắc là chỉ có mấy anh trong ban, rồi với lại chắc là anh Thành sao nhỉ? Ở đây có anh Trần Trí Thành, anh Phạm Như Việt Hà, anh Điền, Trần Hoài Nam, Nguyễn Văn Thái. Biết các anh đấy có ở đầu cầu không nhỉ?
Em có anh Cường ạ.
Việt Hà thì có rồi.
Dạ. Vâng.
Chủ yếu là bây giờ anh
em có online nhưng mà không có join được cái photo section trực tiếp đâu.
À thế à? Tại
Tức
cái
là poster treo ở đấy thì hay là chiếu online?
ở đây không gửi file à? Thế làm sao nhỉ? Bây giờ mình chẳng lẽ mình chụp hình thì mình gửi cho mấy anh này?
Em nghĩ là các anh ở đầu cầu bên đấy thì sẽ chấm poster giúp các
Poster ở đây có anh Thành, anh Điền, Việt Hà và tôi, thì có anh Huy với lại Trần Trì nữa là ký, thì tôi có cô ấy đây rồi, thì có anh Huy nữa thêm vào là thì ở đây không, anh Trần Trí Thành là không thấy được nhỉ? Bây giờ có cái chuyện mình bầu ấy nữa anh Điền ạ.
Tí nữa thì ta sẽ họp các cái chủ tọa, nhưng mà xin anh Hà với thầy Nam và anh Thành cũng như anh Thái hả? Tức là vì các anh các thầy ở ngoài kia không kỹ trên những chỗ, tuy rằng là các anh các thầy là chủ tọa, thì trong này chúng tôi cũng xin phép là ghi chữ ký thay để mà nhưng mà đương nhiên tất cả kết quả thì tí nữa ta sẽ ban để thống nhất chung trong chủ tọa, chứ không phải là chỉ là của ai người ký ý thế. Nhưng nếu những cái tờ giấy đấy thì tôi cứ ký thay với tư cách là trong cái ban chủ tọa của ta để thống nhất để đưa cái hồ sơ cho người ta được, chứ không giờ chuyển các thầy xuống Sài Gòn rồi ra Hà Nội vân vân thì không có thời gian để làm việc đấy nha. Bây giờ thì để tôi nói cái ban tổ chức là phải gửi email, lúc đâu gửi email mấy cái ấy cho các được chứ mà. Ở biết trong biết của email của thầy Hà rồi của thầy Nam, thầy Thái không? Thầy Nam đọc cho tức là gửi cho anh Hà, thầy Thái và anh Thanh thì chắc không biết có anh có dự đầu câu được không, chắc mấy hôm nay anh bận.
anh Thành may đang vào chú ạ.
Hả?
Anh Thành may bay vào Đà Lạt đấy ạ, sáng nay ạ.
Rồi tôi hiểu. Giờ trên máy bay chắc giờ đang học ngoài sân bay. Đúng rồi, máy chuyển chiều bị trưa chắc là vâng. Vậy thôi, cách làm thế nha. Thì như vậy thì thầy Nam bên nhà đợi một tí. Đây ban tổ chức họ sẽ gửi cái slide mà gọi là khổ A0 của cái
Dạ vâng.
poster đấy nha. Còn bọn tôi thì bắt đầu cứ ra ngoài kia chậm trực tiếp luôn. Khoảng 10 giờ thì ta sẽ ngồi lại ta họp tiểu ban. 10 giờ 15 hả? Vâng, 10 giờ 15.